Okay. We started in this chapter to find out how can we find what we call the standard electrode potential, isn't it? The standard electrode potential. Now, what do we mean by the electrode potential? We said that if we have a metal and we place this metal in a solution of its own ions, if we have any metal, if the metal is magnesium, copper, or whatever, and placed in a solution of its own ions, so we say Mn positive aqueous, then a potential difference will be built up between the metal and its solution. What do we mean by this? It means that when the metal is placed in a solution of its own ions, then the metal will start to dissolve, forming the metal ion plus N electrons, and then when the metal dissolves, it will form the positive ions and electrons, and then the positive ions will be attracted to the electrons that are found here, that are left on the metal ion, on the metal, the electrons will be left, and there will be a potential difference between the positive ions in the solution and the electrons on the metal ion. And we said that we cannot measure this potential difference except if we connect this, we call this half cell, or we call it an electrode cell. We call this a half cell. When we connect this half cell to another standard reference electrode, which we call it the hydrogen electrode, we connect it to the hydrogen electrode in order to measure the potential difference between the positive ions and the electrons that are built in this metal surface interface, metal ions metal interface. So this potential difference cannot be directly measured, but in order to measure it, we must connect this half cell containing the metal into its ions to a standard reference electrode. We call it the hydrogen electrode, or it is the type hydrogen electrode. We connect them through a voltmeter, and this voltmeter, as we said, must have a high resistance so that electrons will not flow through the circuit. Only the voltage between the hydrogen electrode and the other half cell is going to be measured, but no electrons will flow and no current will flow. And when we said here standard, it means that we are measuring this potential in standard E at standard conditions. Our standard conditions are that the temperature equal 25 degrees Celsius, any gas has a pressure of 1 atmosphere or 100 kilopascal. All solutions must have concentrations of 1 mole per decimeter cube. Okay, and we said that the standard hydrogen electrode has an E naught value equal to 0. That's why when we measure here the value of the voltage here, it's the standard potential of the standard electrode potential of this electrode, where a metal is dipped in a solution of its own ions. Do you remember how is the construction of the hydrogen electrode, or should I remind you?
Remind me.
Okay, we said that the hydrogen electrode consists of a platinum metal, and at the end we have here what we call platinum porous plate, and this platinum metal, we place it in as if we have a jar like this. We have a jar, a bell jar like this, through which we pass hydrogen. We pass hydrogen gas at 1 atmosphere or 100 kilopascal, and we place this platinum, of course this is platinum wire, and we place it in a solution of hydrogen ions, at which its concentration is 1 mole per decimeter cube. And we connect these two electrodes together. We connect the metal ions electrode with this hydrogen electrode. The pressure, as we said, of hydrogen gas should be 1 atmosphere or 100 kilopascal. And the solution of hydrogen ions at which it is dipped is having a concentration of 1 mole per decimeter cube. And we connect these two half cells together by a voltmeter, which will read us the potential difference between the ions and their electrons in this half electrode or in this half cell electrode. Of course, these two solutions in that way are connected from the outside by the wires and voltmeter, but from inside they are not connected. That's why we have here to add, of course, they should to be this hydrogen electrode should be in this place, and so we connect these two solutions together using what we call a salt bridge. The salt bridge consists of a concentrated solution or saturated solution of potassium nitrate solution. And in that way, the ions will move in the solutions through the salt bridge, and the cell is connected from outward by wires and this voltmeter. And the reading that we get here is the voltage or the standard electrode potential of this electrode. Okay, understand? So if, for example, I have, for example, a metal like, for example, if I have a cell at which a metal of magnesium is placed in a solution of its own ions, which is the magnesium, for example, sulfate. For example, I have a metal of magnesium or zinc, let it be zinc metal in a solution of zinc ions, for example, zinc sulfate, and its concentration is 1 mole per decimeter cube. And we connect it to the standard hydrogen electrode using the voltmeter. We connect them together by a voltmeter. So here we have the standard hydrogen electrode, as we have drawn it from a moment. We pass hydrogen in that way because hydrogen is in the form of a gas, so we cannot put it or connect it directly, a gas, we cannot connect it directly to a half cell. That's why we used this hydrogen electrode connected to the zinc electrode, zinc ions electrode via a potassium nitrate salt bridge. And in that case, as I told you, that the voltage, the voltmeter here has a high resistance in order to not allow electrons to pass through the circuit, because we only want to measure the standard electrode potential of this zinc ions electrode. And so the reading that we get here is that of the standard electrode potential of zinc ions electrode. And the same, if I want to measure the standard electrode potential of another electrode, for example, if I put copper dipped in a solution of its own ions, and also at standard conditions, it means that the concentration of the copper will be 1 mole per decimeter cube, and at a temperature of 25 degrees Celsius. So also the voltage reading that we get here in the voltmeter will be that of the standard electrode potential of the copper ions copper electrode, because it's the one that is connected to the standard hydrogen electrode. Now, what if we don't have a metal that is dipped in a solution of its own ions? What if I want to measure the potential difference between, for example, chlorine plus 2 electrons gives chloride ions? What if I want to measure the potential difference between chlorine and chloride ion in another system? Chlorine, of course, is a gas, and the chloride ion is aqueous. So there's no metal to connect it by wires by a voltmeter to the hydrogen electrode. So what are we going to do? Since this is a gas and the chloride ion is aqueous, it resembles the hydrogen electrode, which has hydrogen gas. And here we have hydrogen ions of 1 mole per decimeter cube, isn't it? They resemble each other because we have a gas with its ions, and also in the hydrogen electrode, we have gas with its ions. So we are going to construct our cell so that we have 2 cells similar to each other, but one of them, now I'm going to draw it first and then show it to you. Okay, so here this is the standard hydrogen electrode. We said that we are going to pass hydrogen. We are going to pass hydrogen at 1 atmosphere or at 100 kilopascal through a solution of hydrogen ions at 1 mole per decimeter cube. And we are going to do the same for the other electrode, but for the other electrode, we have chlorine. I want to pass chlorine gas also at 100 kilopascal or 1 atmosphere through a solution of course, here we have the platinum wire, and we pass it through a solution containing the chloride ions that we want to measure, the potential difference between the chlorine gas passing in a solution of its own ions. So here also the chloride ions are having the concentration of 1 mole per decimeter cube. And since both are gases, we have to construct our cell in that way. We put platinum wires so that we have a metal connected by wires to the voltmeter, which is also a high resistance voltmeter to prevent the passage of electrons or the passage of current through the circuit. And also we have to connect the 2 solutions by the salt bridge. Of course, using potassium nitrate as a saturated solution in this salt bridge to allow for the movement of ions in the 2 solutions. So here, if we have a metal in its solution, then directly we can connect the metal to the voltmeter by wire. But if I have a gas and a solution, how am I going to connect the voltmeter to? So we must use the platinum wire, as platinum is inert. We use the platinum wire, and here we have a high surface area for this platinum plate. Porous platinum, we call it porous platinum. It's porous to increase the surface area so that the reactions would take place. And in that case, the voltage that is measured here in the voltmeter, of course, as the voltage of the hydrogen ion, hydrogen gas electrode is 0, this means that the potential or the voltage that is measured here is the standard electrode potential of the chlorine chloride system. So here, as we said, that the E naught value of the hydrogen ion electrodes is equal to 0. So the voltage that is measured here is that of the standard electrode potential of the zinc ions cell or the copper ion cells. And here also, as the standard electrode potential of the hydrogen ions, hydrogen electrode is also 0. So we will find that the voltage that is read here in the voltmeter will be that of the standard electrode potential of the chlorine chloride system. Understand?
Yes, ma'am.
Okay. Now, what if we want to measure, for example, the potential difference of a system? For example, iron +3 plus electron gives iron +2. Now here we have 2 aqueous solutions. We have two aqueous solutions, and one of them is the iron plus 3, the other is the iron plus 2, and we want to measure the potential difference between the iron plus 3 and iron plus 2. So what do? We also are going to connect this mixture to a standard hydrogen electrode. So our standard hydrogen electrode is the platinum wire that is placed in a solution of hydrogen ion solution. So we pass, as we said before, the hydrogen gas at 1 atmosphere or 100 kilopascal. We pass it through a solution of hydrogen ions at 1 mole per decimeter cube. Okay, and now I want to connect the other solution, which we want to measure its the standard electrode potential between these two ions, the iron plus 3 and the iron plus 2, but both are aqueous solutions. They are not a metal that is placed in a solution of its own ions, nor it is a gas, and we want to measure the electrode potential between this gas and the chloride gas. Then we had to construct a similar system as that of the hydrogen electrode. Here, we don't have neither a gas nor we have a metal. So what are we going to do here? So we are going to construct our cell consisting of a platinum metal. This is the platinum metal. And directly the platinum metal is placed in the mixture of the iron plus 3 and iron plus 2 ions. Of course, every one has a concentration of 1 mole per decimeter cube. This also has a concentration of 1 mole per decimeter cube, so that we get standard conditions. And since both are aqueous solutions, this means that we cannot connect the voltmeter directly to them. That's why we use the platinum metal dipped in this solution of the mixture of both, and we connect this platinum wire to the voltmeter, to the hydrogen electrode, and we do not forget to connect these two solutions by a salt bridge so that the circuit will be closed. So we connect it by a salt bridge, and from which we can measure the potential difference between the iron plus 3 and the iron plus 2, as the E0 cell of the hydrogen ions, hydrogen gas is equal to 0. And this means that the value that we get here in this voltmeter is the standard electrode potential between the iron plus 3 and the iron plus 2 solutions. Okay, or else if we have, for example, a system like that, manganate ions plus 5 electrons plus 8 protons gives Mn plus 2 plus 4 H2O. And we want to measure the potential difference between the manganate ions and the Mn plus 2 ions in this solution. So we will construct a system like this one. But of course, instead of putting iron plus 2 and iron plus 3 aqueous solutions having 1 mole per decimeter cube, we are going to use the manganate ions, the Mn plus 2 ions, and a solution of an acid. Of course, all these are aqueous solutions of manganate ions, of Mn plus 2 ions, and a solution of H positive. All of these have a concentration of 1 mole per decimeter cube. And we connect also these solutions, the 3 of them, by a platinum wire to the voltmeter, to the hydrogen electrode, in order to measure the potential difference or the standard electrode potential between the MnO4 minus and the Mn plus 2 ions. So if we have a metal and we want to measure the standard electrode potential between this metal and its solution, we connect the metal to the standard hydrogen electrode using a high resistance voltmeter. And if we want to connect or if we want to measure the standard electrode potential between a gas and its solution, then we construct this system at which we have these two electrodes resembling each other, because in both of them, we pass gases through their ions. And if we have solutions like this, we want to measure the standard electrode potentials between two ions in a solution, then we put a platinum metal in a solution that contains the ions that we want to measure the standard electrode potential between them. So here either we put iron plus 3 and iron plus 2 solutions, or else for this system, we should add every ions, we should add them as solutions as a mixture, all of them having the same concentration, which is 1 mole per decimeter cube, and we connect them to the standard hydrogen electrode using a voltmeter, and we do not forget about the salt bridge, or else the circuit will not be complete and no reading will be measured here. Okay, understand, or do you have any question?
No, miss, I get it.
Okay, now we said that if we look here, this is the standard hydrogen electrode at which we connect, for example, a magnesium metal dipped in a solution of magnesium sulfate having a standard concentration of 1 mole per decimeter cube. And this is the salt bridge that connect between them. This is the high resistance voltmeter that will not allow the passage of electrons or the passage of current. And as you see here, the platinum, usually the platinum wire, at the end of it, we have a platinum foil covered in porous platinum to increase the surface area so that the reactions will take place. Of course, it depends on the metal that is connected to the standard hydrogen electrode. Sometimes we get here a reading of a negative value, like in case of magnesium when it is placed in a solution of its own ions, we get a negative value, or sometimes we get a positive value. Sometimes we get a positive value, for example, if we have our metal to be copper and dipped in a solution of copper ions, also 1 mole per decimeter cube. What does this mean? That magnesium or zinc have negative values in this voltmeter reading, and copper or silver would have a positive value. The negative value means that we know that magnesium is a reactive metal, and usually we write electrode half cells in the form of reduction. We write like this: magnesium ions plus 2 electrons gives magnesium, and we say that the E naught value is a negative value, negative 0.27, negative point, whatever the value, it's a negative value. What does this negative value mean? It means that magnesium ions would not like to gain electrons to form magnesium metal. Since magnesium metal is a reactive metal, it would prefer to ionize into the magnesium ions and electrons. That's why the E naught value is negative. It means that the metal is a reactive metal and it would like to be in the form of magnesium ions. We say that the equilibrium lies further to the left-hand side. Because it's a reactive metal, it would like to ionize or being oxidized to magnesium ions and electrons. That's why its E naught value is negative. It means that the magnesium metal would like to dissolve, the magnesium would like to dissolve as ions, and electrons would pass. If there was no voltmeter here, we will see that electrons would pass from the magnesium half cell to the hydrogen electrode. That's what is meant by a negative standard electrode potential. It means that this negative value means that the forward reaction is unfavorable, but the backward reaction is. And this means that magnesium metal would prefer to be ionized into the magnesium ion form, and the electrons produced, if there was no voltmeter here, the electrons would pass through the circuit and goes to the hydrogen electrode. But if we get a positive value, like in case of copper, for example, we have copper ions plus 2 electrons gives copper metal. We see that the E node value here will be a positive value, I think 0.34 volts. This is a positive value, which means that the forward reaction is favorable. It means that the forward reaction is favorable, that the copper ions would like to gain electrons to form copper metal. And in that case, we get a positive value in the voltmeter reading, which means that since copper ions in the solution would like to gain electrons, so from where will the electrons come from? They will come from the hydrogen electrode, because in the hydrogen electrode, we have two possibilities. Either the two protons would gain 2 electrons to form hydrogen gas, or the opposite, that the hydrogen gas would ionize to hydrogen ions and electrons. So if the magnesium half cell was connected to the hydrogen electrode, then the magnesium, as we said, would release electrons to the hydrogen electrode. And in that case, the hydrogen ions present in the hydrogen electrode will react with the 2 electrons, forming the bubbles of hydrogen gas that we see here. But if copper half cell, it means that we have a copper metal placed in a solution of its own ions, is connected to the hydrogen electrode, as we said that the copper ions would give a positive value. The system of copper ions, copper would give a positive value in the voltmeter reading, which means that copper ions would prefer to gain electrons to form the copper metal. Since we have a positive value, this means that the forward reaction is feasible. And from where will the copper ions gain their electrons? They will gain it from the hydrogen electrode, that the hydrogen gas that we pass here would ionize to hydrogen ions and we release electrons. And in that case, we will find that the electrons will move through the circuit from the hydrogen electrode towards the copper electrode. That's why it has a positive value here in the voltmeter. Understand, or shall I repeat anything?
Understood.
Okay, so this, how do we measure what we call the standard hydrogen electrode? As you see that some half cells would have positive values, like in case of silver ion plus, always we write the half cells in the form of reduction form. So they have positive values, but if we have negative values, this means that the opposite reaction is the favorable. The reaction shifts towards the left-hand side, or the favorable reaction is the shifting of the equilibrium towards the left-hand side. That's why we get negative value. Of course, the more the negative value, the more the metal would tend to go in the backward direction, or the equilibrium would favor the backward direction. And for the standard hydrogen electrode, the E node value is always 0. Okay. Now, this is, as I told you, when we have a chlorine chloride, we want to measure the chlorine chloride standard electrode potential system. We connect it to the hydrogen, the standard hydrogen electrode, as we said. And the E node value is positive 1.36 volts, which means that this electrode, the direction of the equilibrium for this electrode cell would be favored to the right-hand side. That's why the E node value is 1.36, which means that the chlorine would gain electrons from the standard hydrogen electrode so that it is reduced to the chloride ion. And when we have a mixture of iron plus 3 and iron plus 2, we just connect the platinum wire to the platinum foil covered in porous platinum to the standard hydrogen electrode using the voltmeter. And we get different half cell reactions and different standard electrode potentials by being measured, every one of them by being measured against the standard hydrogen electrode. And in this case, they are arranged in the form of what we call the electrochemical series, at which the more negative values are placed, and then the less negative or the more positive until we get the most positive values. If we look at this table, we can look at it here. It's the same table. We can see that as lithium ions plus electron gives lithium metal has the most negative value, this means that the forward reaction is completely forbidden, or it's not favorable at all. But the opposite is the one to be favorable, that the lithium would return back into, or would give lithium ions plus electron is the favorable one. And since lithium would prefer to give up electrons to form lithium ion, it means that it is acting as a reducing agent, because as we know, reducing agents give electrons to whatever is beside them. It's a reducing agent as it reduces what is beside it. How will it reduce it? It will reduce it by giving it electrons. So the lithium here is the strongest reducing agent. It has the greatest negative value for E naught. Since it has the greatest negative value, it means that the lithium favors the formation of lithium ions and electrons the most, which means that it is the strongest reducing agent among all these, because it had the greatest negative value. And this means that lithium, potassium, calcium, sodium, aluminium, zinc, and chromium, and iron, all these metals would act as reducing agents. But of course, the most powerful of them is the lithium. All of them, as they have negative values for the standard electrode potential, it means that their equilibrium will lie further to the left-hand side. And this means that all of them would prefer to lose electrons, not to gain electrons. And so they are acting as reducing agents. But the reduction power of lithium is the greatest. And if we look at these elements below the hydrogen, we find that the values are positive, and the positive value increases as we go down here in this series, which means that the most element or the most species that will have the greatest positive value is that of the fluoride ion. It means that fluorine would like to gain electrons to form the fluoride ion. So here we say that fluorine is the most powerful. It is the most powerful oxidizing agent, because its oxidizing agent, it would like to gain electrons. It's going to be reduced, as it is an oxidizing agent, it's going to gain electrons. And so this is the most powerful oxidizing agent. So here we have reducing agents up till iron. These are reducing agents. But from the other side here, starting from copper ions, we have oxidizing agents. But the most powerful of them is the fluorine gas. Fluorine gas, طبعا, when it passes through a liquid, it forms fluorine aqueous solution. Then this is the most powerful oxidizing agent. All these are oxidizing agents, but the most powerful of them is the fluorine, because it has a great tendency to gain electrons to form the fluoride ions. This is obvious from the large positive value in the E naught value. Okay? Understand, or do you have any question?
Understood.
Okay. So as we said here, all these are reducing agents. All of them are reducing agents, but the most powerful of them is lithium. And all these are oxidizing agents on the left-hand side, but the most powerful oxidizing agent would be the fluorine. Now, we come to what we call the electrochemical cells. What are electrochemical cells? Electrochemical cells is when we connect two different electrodes together. Now, we measured the standard electrode potential of zinc alone with the standard hydrogen electrode, and we measured the standard electrode potential of copper alone with the standard hydrogen electrode.